Okay, so today's lecture is going to be on MPI parallelization strategy. So this is the, it's a very complex argument. So it's going to, I'm going to spend a little bit of time on this part. And it's these two lectures. So the shared parallelization and the MPI parallelization are going to be I think they are the most difficult things to understand for somebody using libraries like DL2. So please, if you think it's very difficult, don't be so worried, because it is actually difficult. So it's not something that you're expected to understand in 2 weeks. But the idea behind this module is to try to make you understand and to appreciate how in reality, if you understand what is the principle behind, you don't need to know everything that is happening behind the scenes. We will give some hints, and we will try to take a look at how things actually work with a very short program that I've also included in the exercises. But apart from that, the way that codes look in the DL2 library for the examples when they are run in parallel on fully distributed mechanisms is very similar to the way that they look in serial. And the reason why that's the case is because the paradigm that is used in DL2 is to try to hide everything that is hideable in the background in terms of MPI parallelizations, so in terms of communications, in terms of the details of how to build the actual distributed grid and so on and so forth. So today we're just going to be doing a very first introduction. We're going to basically try to translate what we have done in the person.cc file to something that looks like step 40. And the arguments are how to do parallel distribution of degrees of freedom, what is the ownership concepts in distributed computations, how to set up data structures for parallel processing, how to assemble in parallel, and the synchronization of distributed data, as well as the visualization of data. All of these things would take a year to master and to implement from scratch. So the fact that you're using a library like DL2 allows you to basically jump right into using those tools. So I'm not going to teach you about how to work with MPI efficiently. I'm going to teach you how to use a library that works with MPI efficiently. So it's the focus of this lecture is not shifted towards learning how to do HPC computations or how to program in HPC, but it's how to use a library that actually does that. Otherwise, you would have gone to the master performance computing, therefore the full course of the master performance computing. That's the goal for that. Also, for this course, we want to learn how to use these tools that are implemented for us. Tutorials, step 17, step 18 are the first tutorials in which we have some parallel implementations going on with distributed and with MPI. Video lectures by Wolfgang, these are very, very useful if you want to. And then there is a very large tutorial part here, which is the distributed documentation of the DL2 library, which is what I'm going to be using as a reference material. So what's the idea behind MPI computing? Well, the idea behind MPI computing is that you basically run multiple copies of your program, same program, multiple copies, and you identify each one of the participating process with the process ID in a certain sense. And so the idea here is that, however, you do not have access to the same memory. So you cannot assemble the sparse matrix on your memory and assume that everybody else has access to the memory. You don't have that because you have separate computers, possibly on separate rooms or possibly on separate states. So it doesn't really need to be close and local. Of course, every time you need to learn something from another participating process or from another computer, you need some communication. And this is called, it's the paradigm behind this is called message passing interface. And it's a standardization that has been around for a very long time that actually tells you how to execute this type of communication between participating processes. How to do this efficiently, that's another, it's an entirely different story. And in particular, the way this actually works on large computing clusters is by having a special network, which is dedicated to the communication between processes that are participating. This network is not the same type of networks where the internet runs on, because it's a very fast optical network. And in some sense, the speed of this network is faster with respect to accessing disk, but you have to consider this as a bottleneck of your program. So the essential part, in general, is that you don't always need to do this. So if your goal is to run a two-dimensional simulation, and you're running these simulations with less than a couple of million degrees of freedom, you don't need to run on MPI. That's the main issue and the main important things that you need to do. Of course, if you need to run larger scale problems, like for example, you want to have something that runs for very long times, like for example, time-dependent problems on three-dimensional domains, in which the number of degrees of freedom may be going up to 60 million degrees of freedom, a billion degree of freedoms, then in these particular cases, you might need to split the work. And you will not even be able to probably to store everything that you need to have on a single memory. So you frequently swap from the memory to the disk, and you might just as well do that by splitting also the work between several computers. So general considerations for MPI and for parallel computing, you just want to get the solution faster. So if you do finite elements with less than 500,000 DoFs, just use a direct solver. Otherwise, you need to split the work. So distributed storage, it means that every computer, every node, every participating process only has access to local structures, so to some of the parts that are owned locally. And of course, you need to have data structures that know about this, and you need to know how to communicate data between various parts. And this is where things become complicated. So we will see how to do this for a very, very simple example of the hello world using MPI. But apart from that, the essential things that you need to understand is that all of this has been written for you by somebody that has been working on this for a very long time. So you don't need to learn how to do these things, you just need to learn how to use those things. And of course, the main idea is to localize and hide all the possible communication and to use as much as possible point-to-point communication. So I don't want to do global communications, because by global communication, I mean, if you have 10 participating processes, so you run 10 copies of the same program, you don't want ever that every process in the run communicates to every other process. That's called the global communication or broadcast communication. You want to restrict communications to point-to-point, saying, for example, I am process number 0, and I only need to get with process number 1, and that's going to be just exchange between me and number 1, and maybe number 2 is communicating with number 3, and number 1 is communicating with me and with number 5, say, for example. Of course, when you do this, you want more that the communication is not blocking. So that means you don't need to wait for the communication to start, to be finished before you do something else. And this comes back very similar to the way that we have been doing in the past, the way that we have been showing for the shared communication part. And so you have to understand how these things fall into pieces together, and you have to understand what are the things that need to be changed in the library and in the code in order for this to work. So let's take a quick look about what we have in the code. In the code, what happens is that you don't parallelize things that happen on a single cell. So basically, what we are assuming is that every single process owns, in some sense, some of the cells and knows how to work on some of the cells. So everything that is localized in terms of unit cells, finite elements, quadratures, mappings, everything that needs to be used in a single cell is replicated on each of the participating process. All of the other guys, however, need to know, for example, what part of the domain I'm working on, what part of the domain I own in a certain sense. And the DoF handler needs to know how to distribute degrees of freedom. The linear algebra needs to know who owns parts of what part of the matrix, and so on and so forth. So all of these guys that I wrote here in blue are guys that need to be somewhat aware of what is happening in the background. So this is these things are difficult to do efficiently when you want to work in parallel. So the first thing you have to ask yourself, what is really happening and that you want to do? So what's really happening If you want to work with this in terms of the partial differential equations, what's happening is you're splitting the domain on which you're solving your PDE onto subdomains. Say, for example, omega-1 and omega-2, and there's a boundary between omega-1 and omega-2. That's one option. You can do that. And you run on two computers. One solves the problem on omega-1, and one solves the problem on omega-2. If you are good at doing this, and if you know how to transfer solutions between the surface gamma, and you know how to exchange information about this, then you're perfectly fine with this. And this is usually called domain decomposition method. And there's a lot of literature that tells you how to do properly domain decomposition method. And of course, you have to be careful with these types of things, because there's a lot of issues that come into how to actually make sure that the global solution converges to the solution that you would have had without splitting the problem in two parts. And some of these things are very complicated. There's no black box approach. You have to write everything from scratch for yourself. And in order to have efficient solvers, this is going to be very difficult if you scale with the large number of CPUs. So you have to be you have to be aware of the fact that if you do not have a coarse grid solvers, that's the way they are called, or a solver that actually solves a coarse problem on the full domain, you're not going to be able to get optimal scaling with the number of CPUs. And this is an issue which makes this approach less amenable and less attractive from the point of view of the implementation. The second option, which is what is used in the library, in the DL2 library by default, is the so-called algebraic splitting option. And so the thing is, you logically, you know there is a full grid on the background, so a locally refined grid in the background. And what you do is you split the work on different grids, but then logically, you assemble a global linear system, which is assembled but not stored entirely on every single processor. Every single processor only stores parts of the global system. So what that means, for example, process number 0, which is the one that is depicted, that owns the red cells here, for example, just as a simple example, will own the corresponding entries in the matrix that refer to the red cells. And instead, the yellow processor here will own the corresponding lines in the matrices and in the vectors that correspond to this part. And the only thing that you need to do at this point is you need to be able to communicate maybe sometimes at the boundary of the domain. So you only need to have local point-to-point communication between neighboring subdomains. And of course, when you perform the matrix vector multiplication, you have to do some communication, because you will have to make sure that this communication happens when you perform the global matrix vector multiplication. However, most of this is going to be local, and you'll only have some communication if you have a sparse system that refers to some degrees of freedom. And this can be done very efficiently, and there's a lot of libraries that do this very efficiently. And the advantage of using this approach is that you can leverage external libraries for that. And the only thing that is left for you, in a certain sense, is to understand how to partition the domain. So the partitioning of the domain is a difficult problem if you want to do this globally and efficiently. And so the optimal partitioning would like to have two options, two ideal goal, and to have basically the same size of the number of cells per domain or per region, in such a way that when you do the local assembly, for example, you would have a balanced workload between the process that owns the yellow cells and the process that owns the red cells. So in this particular case, you would have, for example, the process number 0 owns 4 cells and process number 1 owns 3 cells. This is rather balanced. You cannot do better than that, since this is you have an even number of cells. And if you want to do this for a very large number of processors in a very large domain, it might be much more difficult. So this is an NP hard problem, graph partitioning problem. So there's a lot of tools that allow you to do that heuristically. And the goal that they try to achieve is to have a balanced distribution of the work, so a balanced number of cells on the different regions, and they try to minimize the interface between the region. So this, as a main goal, distribution of work. So you want to make sure that everybody does the same work roughly, and this instead tries to reduce communication as much as possible. So if you make the smallest area around this part, you reduce the communication between these things. Okay, so if you want to do this heuristically, you have to use external tools. Metis is one option, and what we support Metis, but this is very inefficient for large computations. So the other things that we support is called partitioning using space filling curves. So space filling curves are basically algorithms that allow you to cover full space in 3 dimensions or in 2 dimensions or in 1 dimensions with a single line. So it's a curve, as the name says, you split the 3-dimensional domain into a long 1-dimensional line, and then splitting the work simply is equivalent to cutting the lines on equal lengths. And so you transfer the problem of splitting the domain into areas to the problem of cutting a line, a 1-dimensional line. And if you choose the space filling curves algorithms in a smart way, then what happens is that they have a spatial locality. So basically, near points on the curve are also near in terms of the embedding space, and they are very easy to do, and they scale very good. The main issue between this, the main difficulties about this is that simply you don't have the optimal number of so the optimal boundary size, because you might have some inefficiency with respect to the size of the boundaries between different regions. So this is an issue, but it's not such a big issue, and so the advantages of using these types of partitioning schemes is much larger with respect to disadvantages. So this is what we use in the library, and we use the library that is called pForest, which stands for a parallel forest of trees, which is parallel forest of trees for quad and octrees. And this is for the 3-dimensional grids based on quadrilaterals and hexahedrals. If you want to do triangles and tetrahedra, you have to use something else like lattice or something else, because there's no quad tree and octree splitting in terms of pForest for those particular cases. So how does this work? Well, simply in the following way: you consider every single cell of your triangulation and the children of the triangulations as a forest of trees on which the nodes are the cells and the leaves are the children of those cells. So if you look, for example, of a deductively refined grid, the main node which is here is the background cells that you see in the back. Right? So this background cell that you see in the back is the main node of this graph. And it has 4 children, which is 1, 2, 3, and 4, or by number, and this would be number 1. In this graph, it's number 1 here, 2, 3, and 4, and this is graph number 1, 2, 3, and 4. And number 1 again has 4 children. These guys over here, which is 1, 2, 3, and 4. And if you use Z ordering, which is what it's used here, then the Z ordering means you just draw a Z on each one of these guys, and you draw a Z on each one of those guys, and then you just order those guys in such a way that there's locality there. Now, splitting the domain at this point simply means to cut this line in a balanced manner. And so, for example, here you cut either at 3 or at 4, and you try not to cut on children. So you try to keep children on the same area. So the only place you want to cut is this pathway here. So this is exactly what happened in this particular case. Cut here, and you have processor number 1 here, and processor number 2 here. This graph partitioning algorithm is extremely simple, and you can replicate the tree with a very cheap data structure on each one of the processors. So each one of the processor knows, in principle, how to reconstruct the full grid, but only reconstructs the grid that it has. So in particular case, the data structures is shared among all processors, and the reconstruction of the actual triangulation is only done for the path that you locally own. So it's difficult to understand this without looking at the pictures. So let me show you a picture that shows you how this actually works. So this is, for example, a locally refined grid, and you have color by CPU ID. So CPU 0, CPU 1, which is the yellow part, CPU 2. And in this particular case, what we see here is that we split the domain using Z orders. And so you basically have a space filling curve that fills the full space here, and the space is 2-dimensional here. And then it cuts this curve into 3 equally spaced. So three equal length segments, and each one of the processor knows which segments it has to use in order to reconstruct the actual structure of the triangulation, and it reconstructs everything up to the current local triangulation with some artificial cells here that you see in white that are required in order to get a valid triangulation in DL2, meaning you always need to have a balanced number of neighbors in terms of hanging nodes. So we only allow one hanging node per face. And if you do that, if you want to reconstruct this grid, you also have to have these artificial cells here. And the advantage of doing it in this way is that locally you have, so the sum of these three guys is the same as the global triangulation. However, processor number 0 knows nothing about what happens in the white region here, while processor number 1 knows nothing about what happens in this white region, and processor number 2 knows nothing about what happens in this white region. The only thing that they know is that you understand, and you are aware of, you have access to all the degrees of freedom that pertain to your own area, plus one layer of ghost cells. Those are called ghost cells over here. And one layer of ghost cells is what is required for you to be able to compute, for example, error estimators, or to actually assemble the cells locally, or to read values of the degrees of freedom locally. So you have to be you have to have an accurate reconstruction of the grid up to the first layer of cells, which is outside your owned part of the cells, and you own the part of the cells which is red here, yellow here, and blue here. Okay. So what's needed for this to work? Well, in principle, not much. So in the code, you'll see you just replace the triangulation by a parallel distributed triangulation. You create or load the mesh as usual, so nothing changes. And then you adapt all of the various grid refinement, refining cosin, and execute cosin refinement in order to work with the parallel version of triangulation. And then the only thing that you have to be careful about is that you can only access degrees of freedom, and you can only access and assemble things where you have locally owned cells, or maybe the ghost cells on the neighbor cells. You cannot do anything else outside. So there's artificial cells, which are the white cells that you see here. All of these white cells are just artificial in the sense that they are there in order for you to have a fully working and a fully consolidated DL2 triangulation structure, and interpret this DL2 triangulation structure as a parallel distributed triangulation in which you only know how to work with the locally owned degrees of freedom, locally owned cells. Okay, so every process sees the full triangulation, but is only allowed to work on the part of the cells that are locally owned. This overhead here that you see, the white triangulation, is negligible. It's less than 5%, even up to several billion degrees of freedom. So this is not an issue in terms of memory footprint, but it allows you to simplify a lot everything that is there. So this is one idea. Okay. After you have done that, dealing with degrees of freedom and the linear algebra changes. So this is more complicated. It's not something that you have to know how to understand in details, but you have to understand what is happening in the background in order to understand what type of function calls you need to call. So this is what we're going to try to understand today. So the idea here, let's give you a sketch, is in order to create a global numbering for all the degrees of freedom is, well, the idea is that you create a global numbering for all of the degrees of freedoms, and you identify the ones that actually fall within your own cells, and you try to keep them locally to your own cells. And you try to do the numbering in such a way that local degrees of freedom are close to each other. And then you exchange the number of degrees of freedom that you have with all the participating processes. So there is one global communications that only communicates the bounds of the number of degrees of freedom that you have locally. And once you have done that, you need to understand, you need to match what are the boundary of the domain. So the degrees of freedom that are on the boundaries between two bytes, and you need to communicate to your neighbors, look, I will need to access data that is owned by you. Please keep me in mind when you do changes on your part of the process. Okay. So in principle, This is very complicated if you want to do from scratch. And luckily, the degrees of freedom handler, so the DoF handler class, understands whether it's dealing with a shared distributed triangulation or a parallel distributed triangulation. And when it sees that this is the type of triangulation that it's using, it does some communications in the background so that whenever you query things for this degrees of freedom to the DoF handler will respond with the global data and not the local data. Okay, so there's a distinction between local data and global data that happens in the background. And from the perspective of the user, to you, it looks like it's serial, with the exception that you're not accessing all the cells, just a part of the cells, and somebody else is accessing the next part of the cells. Other things need to change. You need to change the solvers. So all of this needs to become parallel objects, and we use external libraries to do that. And once you do this, the solvers just look exactly like the same, because the only thing that needs, if you don't have access to all the triangulation, but only to the matrix vector product, the matrix vector product can be done independently, whether the local vectors or the local matrices are actually owned by everybody. The only thing that you need to compute at some point will be scalar product vectors. And this is, again, something that's taken care of by the library that actually does that for you. So at the end, it's really not a matter, you don't need to implement anything with this part. You just need to understand that some of the parts of the vectors will not be yours, will be owned by somebody else, and will be split into equal sizes or roughly equal sizes between the participating processes. So again, also vectors and matrices will be objects that look which are opaque to you. So you only see of these objects local entries or locally owned entries. So you have to initialize these objects differently. Of course, you can no longer say, I want a vector which is end-of size. You need to say, I need a vector which is end-of size, and of these end-offs, I need a set of sub-indices which are the ones that I own, and this is the way that we're going to initialize this. So we will use the concept of index sets, or which are sets of indices that we own. And we will need to have two different types of vectors, one which is for reading and one which is for writing, and we will go into the details from this on. Just to give you an idea of how this actually works, this is a strong scaling of step 40. So this is a Poisson solver that is run on 16,000 processors on this supercomputing center in Munich. And almost everything scales perfectly except for the linear solver. And the linear solver doesn't scale well because preconditioning these types of systems is very complicated. And we use algebraic multigrid for these things. And the essential part of this is that you need to have a sort of a coarse structure that is known and that is distributed among all processors. So in order to be able to produce a optimal solution, the solver is the most complicated. But there's active research going on into trying to construct a solver which are optimal. And so far as we are concerned, we are going to be using algebraic multigrid in order to linearize, in order to perform the preconditioning of the system, and this scales rather well up to quite a large number of processors. And of course, this is not good scaling, but up to this point here, so up to a few thousand processes, this is actually quite efficient. This is called strong scaling. And it's called strong scaling, meaning that you start with the vector with the problem size which is fixed, and then you double the number of the number of processes with which you try to solve this problem. So this is a 335 million degrees of freedom, and you solve it on 128 processors. Then you double the number of processors, and if you had perfect scaling, which is this, you would expect doubling the number of processors to halve the number of the time that you take to solve. Yeah? And of course, you see some of those things actually take half of the time. So for example, assembly is almost perfect. The initialization of the matrix, it's not so perfect because you need to do some communication. Sparsity pattern is not so perfect because you need some communication. The copy to deal to error estimation, assembly, and so on and so forth. So all of this seems to scale quite well compared to the optimal scaling. And the only thing that is actually not working so well is the linear solver, because you will need more and more iterations to solve when you have a much larger number of degrees of freedom. And weak scaling instead is the memory consumption. This is the memory that is occupied on each one of the CPU. So on the average memory that is occupied on each one of the participating CPU, and the maximum memory that is occupied. And as you see, splitting this in terms of 1016 processor or having just 8 processor, the difference between this is not so large. Okay. So this part over here and this part over here, they look very similar. So this means that you can actually scale with very large number of CPUs. And this is actually weak scalability. So it goes from 8 to 1000 processor. And in 2D, whenever you go from 8 to 16, you're doubling the number of CPUs and you're doubling the number of degrees of freedom in order to make sure that every CPU actually works on the same number of degrees of freedom. So in constant memory usage, increasing CPUs and problem size. So when you go from here to here, you make sure that you have the same increasing number of CPUs in order to compare with apples with apples. And if you look at the terms of weak scaling in terms of wall clock time, you'll see that this is actually very efficient. So this is why we want to use these types of problems. So we want to be able to solve larger and larger problems, and we want to be able to do that in a more and more efficient way. Okay. We use 2 different types of libraries to do linear algebra in the background, either Trilinos or PETSC, and we can choose both. And I think some prefer Trilinos, some prefer PETSC. In terms of usage in the library deal 2, they're basically interchangeable. So there is not much of a difference in these 2 cases. I think PETSC also has access to very good eigenvalue solvers. So if you need to solve eigenvalue problems, maybe PETSC has some very good usage for you. Trilinos, on the other hand, has a little bit more modern as an architecture, and it has some advantages with respect to PETSC. For example, Trilinos also supports multi-threaded parallelizations together with MPI parallelization, while PETSC is not multi-thread safe. So if you want to do multi-threaded parallelizations and MPI parallelization at the same time, you should use Trilinos. If you want to use just MPI, you should use PETSC. The difference between the 2 is not so large, and you'll have the chance to change these things. So how to use these 2 in the library? If you look at step 40, there's a include files that is called generic linear algebra that defines in the namespace linear algebra PETSC, linear algebra Trilinos. It basically defines the same type of objects with a different backend implementation. So the idea is that using serial vectors or distributed vectors is basically the same except for initialization types. So initialization is slightly different when you use MPI or non-MPI, but except for that, you can use PETSC or Trilinos simply by using a different type of namespace, like in the case that we have here. So we will exactly do this. So let's try to go a little bit more in the detail of how we do this in parallel. So what is needed in parallel for a triangulation to understand how to distribute degrees of freedom and how to do the partitioning of the degrees of freedom, and to understand exactly why we need 2 types of vectors and why we need 2 types of different approaches. Okay, so distribution of degrees of freedom and colorization via graph partitioner, for example, this particular case. So let's assume that we have this triangulation, and the triangulation is split into 2 parts at the moment. One part which is coarse and one part which is finer. And we assume we have 3 participating processes. Of course, this is not a realistic example. You will never want to have one process working on 3 degrees of freedom. You want to have one process working on 3 million degrees of freedom. But this is just to give you the idea of what's going on in the background. So process 0, process 1, and process 2. Okay. And now, in some sense, the degrees of freedom handler needs to know which ones are the degrees of freedom which are associated to process 0. So in this particular case, I'm assuming that I am using Q1 finite element methods. So Q1 finite elements, so 1 degree of freedom per vertex. Okay. And in some sense, we have to decide how to split this. So let's assume that the partitioner does that for us. And so we end up with this type of balanced workload. So we have 3 degrees of freedom in process 0, 4 for process 1, and 3 for process 2. Okay. And now, of course, we have a problem in the sense that if you want to assemble something that depends on the solution locally here, process 0 needs to have access also to these 2 little dots over here. So if you look at the owned degrees of freedom, process 0 only owns these guys, process 1 owns these guys, and process 2 owns these guys. And so here comes the first difficulties that you have to keep in mind when you do the parallel, when you go from serial to parallel. So when you go from serial to parallel, you own a cell, but you do not own all the degrees of freedoms that belong to that cell, possibly. And so you need to have access to the neighboring cells as well. If you're on the boundary between two processes, like in this particular case, then you will often need to have access to these guys over here. So if you look at the terminology used in deal 2, those guys, the one that I'm now circling with brackets, with the lines, are locally owned degrees of freedom, while the ones that are used, for example, for assembly or to output data, these are called locally relevant degrees of freedom. And the locally relevant degrees of freedom for process 0 are all the ones that are that share at least 1 degree of freedom with the owned cells. And of course, the hanging nodes does not belong to this guy because this doesn't know about the hanging nodes. The hanging nodes belong to, logically belongs to the other paths. So this guy here, for example, needs access to 1, 2, 3, and 4. So it will also need to access this guy as a locally relevant degrees of freedom to produce, for example, output or to produce some error estimates. Okay, so for the output, you need this. But if you need, for example, to compute the gradients on the face or the jump of the gradients on the face, you need to have access to all degrees of freedom here, but also to all degrees of freedom here, because the jump of the gradients of a solution, so if you have a solution vector U, you will need to have access also to the degrees of freedom associated with these 4 points. So if you actually look at this, for the Kelly error estimator, you need to have access to all of these guys. And this is just for process 0. Of course, in this very bad example, if you look at what are the locally relevant degrees of freedom for process 1, which are these guys, well, basically everybody is a locally relevant degrees of freedom for process 1, because here I will need to have access to the gradients of the solution that come from this side to compute the jumps and the gradients in this phase. And in order to be able to do that, I need to have access to these 3 degrees of freedom as well, because the gradients here depends on all of those 3s. And basically this, everything is relevant for that guy. And now if I look at just at process 2, for example, for process 2, the locally relevant degrees of freedom are only the ones that share the degrees of freedoms that belong to all the neighboring cells. Okay. So process number 2, we'll have to communicate with process number 1. We'll have to ask process number 1 what are the values of the blue guys, and to process 0 what is the value of the red guy, of the black guys. So what are the changes that we need to do in the code in order for this to work? We'll do this together. We'll move Poisson.tc to a parallel version of Poisson.tc in the examples that we have. Okay. New headers. So we need to include MPI. We filter this through deal 2 in the sense that if you don't have MPI installed, this will define fake entries that will make your code look the same in the serial case or in the parallel case. And this is a parallel shared triangulation. We will use not a parallel shared, but a parallel distributed. So this will be parallel deal 2 distributed, parallel distributed read. We will need to filter iterators. We will need to iterate only on locally owned cells if you want to do mixed parallelization strategies. We will need to have a knowledge of subsets of indices which are owned locally in terms of, for example, degrees of freedom, and in terms of vectors, and in terms of linear algebra. We use Trilinos linear algebra, output filters, and so on and so forth. Right? So these guys over here are a new set of headers that will be included in the library, included in the actual solver. So class definitions, we need to have an MPI communicator. An MPI communicator is an object. We will see how this works in the hello world for MPI. It's a basically data, well, it's if you look at it internally, it's a integer. We don't really care about what this actually is in real life, but it's an object that MPI uses to understand, for example, how many processors are available for the communication, how many copies of the same program are being run at the same time, and what is the rank of the current processor with respect to the total number of processes. That means, for example, that MPI, the library that uses message passing interfaces, will give information to each one of the running processes about who they are with respect to the total number of processes, what is the number of total processes to run, and so on and so forth. And we will be using a lot of these guys in order to construct, for example, stream filters, so things that output only when your process number is equal to 0, and so on and so forth. We will need to change the type of triangulations and the type of sparsely linear algebra objects, and we will need to introduce locally owned degrees of freedom, locally relevant. And of course, when you assemble system matrices, or when you assemble, for example, right-hand sides or right-hand side vectors, or when you assemble error vectors, you have to make sure that you access data that you can access. And if you access locally owned data, everything is fine. If you need to access data that is not yours, you can do so only if you first communicate this data. And that's why we will need two different databases. Okay? And I'll show you how this actually happens in the library. So first of all, we must determine what are the set of locally owned and locally relevant degrees of freedom. So the locally owned are those assigned to a particular MPI process, and the locally relevant are those that are assigned to other processor but are required to perform some action on the current process, for example, evaluating values of gradients. And we need to distribute the sparsity pattern, because I need to tell other processors who I'm communicating with in terms of local degrees of freedom. So if the local degrees of freedom that I have on a single matrix, on a single entries of the matrix need to, for example, it has in the matrix communication with something that does not belong to my processor, I have to communicate that to the next processor. Okay. So there's a lot of these guys over here that needs to be changed in order for things to work. And you will see some of this look very harmless, and some of this are very difficult to understand and very difficult to write if you don't do things correctly. So we will experiment a little bit with this, and we will try to understand what the main errors actually do. So how do we change the assembly? Well, the assembly will look very similar, with the only one exception. We only loop over cells that are owned by the local MPI process. You can use filter iterators, or you can check within the cell loop if your cell is locally owned. Okay. And all the assembled data is initially localized to a single process, and then you synchronize everything between various participating MPI processes at the end of the matrix. And the way this is done is by calling compress, a function which is called compress in the yield2 library terminology. And this function here actually make sure that I communicate to all of the participating processes that I want to add some more entries, for example, because I'm assembling the local right-hand side on some terms that do not belong to me, and I will collect from all the processes exactly what needs to be communicated to me. Okay, so this accumulation of values is done only once, and this is exactly what we need to change. And then we need to change the type of solvers, because it's templated on the vector type, so it's not really very complicated. You just need to specify that you want to use a certain type of solvers. And mesh refinement needs to be changed a little bit, because the Kelly error estimators need to know the solution on the values that are not owned by the current MPI process. So you cannot call it on the same vector that you have used to assemble the system, but you used to solve the system, because those vectors only know about the locally owned vectors. And you need to provide a solution with something that contains everything that is required for the actual computation of the error. Okay. And then post-processing also will change. You have to write out the portion of the solution from each processor. So on each processor needs to write a part of the solution and not all of the solutions. This DO2 writes this on a per cell basis. So if you're in a single cell, you need to have something which is, you need to know everything about that single cell, including things that you don't actually own. So if you try to call this with the wrong types of vectors, you will get errors, which are usually easy to catch in debug mode. Okay? And then the last but not least, you need to initialize MPI and to set up MPI. This is something that is done using MPI initialize and finalize here and there. Okay. let's dive into the actual implementation, and let's try to understand how this actually works for the examples that we have here. So you can find this in Lab 8. I have uploaded this link on the GitHub Classroom, and let me start sharing the other screen, and we can actually take a look at live on the other thing. Okay, so share screen. Desktop number 1. You should see now the desktop with the actual code. Okay. So this is laboratory number 8. And this is the second to last laboratory. So last laboratory will be number 10, and then we'll do a small project. So the plan for the next part of the course in terms of programming is to allow you to solve vector value problem in parallel on the library, and we will spend one lecture in doing vector value problem, in particular Stokes problem, and in parallel. And the last lecture will be spent in trying to understand how to do complicated preconditioners and how to write preconditioners for complicated problems. Those two are particularly useful sets and tools to have, because otherwise you will not be able to solve real life problems. So if you look at the README of this laboratory number 8, which should be available as GitHub Classroom number 08. I should have probably named it differently. So this is 08 MPI parallelism with dash. What's it called? CISA MHPC Lab 08. Update. Sorry. And you should have already the link. Marco has already accepted everything. Good. This is the list of all the things that you have, and this should be present also on the links at the end of it. So if you click there, you should be able to accept the assignment that I have here. Okay, so first of all, I wanted to take a look together with you to the MPI example that I've called MPI hello that is written here. So let's take a look at the MPI hello that is written here. So MPI, this is a very trivial MPI program that actually uses only MPI, native MPI libraries, not DO2 libraries, just to give you an idea of how the MPI world actually works. So this is the include file that allows you to do to use the message passing interface libraries. For every MPI program, before you do anything, or before you use any of the MPI based functions, you have to initialize the MPI world. This MPI init does exactly that. So it reads the arguments that you pass to the command line. And these arguments are pruned by any MPI related activity or any MPI related comment. And it's the essential part of this is that if you want to run an MPI generated, an MPI aware code, you have to use MPI run as a prefix to run these guys. So you don't just run the code as you would do normally. What you do is you run the code through MPI, because MPI needs to know, the system needs to know how many processes you want to run, how many copies of the same process you want to run, and it needs to assign to each process its rank inside the world. So this is done by the MPI exec or MPI run utilities, and these are two executables that come together with MPI compilers and the MPI library on the outside. So in a particular case, we are using OpenMPI, but the standard here is very similar no matter what type of library you use. MPI CH is another option, or Intel MPI, it's another option. So here, what happens is I initialize MPI, And this detects whether you have run the code through MPI exec or not. So let me just do this manually. So if I enter the sysMPI lab 08 and MP hello, and do simulate dot, and I do make. This will generate an object which is called main. If I run main, it will say something. Hi, I am process 0 of 1, and I'm running on Wolverine.live, and nothing seems to be particularly strange with the way that I run this guy. And now let's take a look at the code, and let's try to understand what is happening here. So the code is running a few commands before actually outputting something. Okay, so the first thing it does, it creates an object which is called rank and an object which is called size, and then it calls functions of MPI that fill those two guys, rank and size, using a global name which is called MPI convolt, and this guy is defined on MPI.page. So this tells you the following thing: I initialize MPI, and once I have initialized MPI globally, I will have access to a communicator. So this is the way that this is called in the world in the terms of MPI. And this communicator object knows about who is working with whom, how many processes we have, and who is participating on this number of processes. Yeah? And in particular, these functions here check who the communicator, ask the communicator, and inside the communicator, or according to what's written inside these guys over here, they can extract what is your rank and what is the total number of processes that are participating in these type of things. So at the moment, I ran this just once. I just ran one single copy of this program. I did not run multiple copies of this. So it only said, okay, I'm processor number 0, which is the rank of this process, of number 1. So that says there's only one process running. And I'm running on processor name is just MPI name length is get processor name. It's returned to, this is another function of MPI that gives you some more information about who I'm running on. If you try to run this on Ulysses, for example, and you try to run this by asking for 50 processes, and you run using MPI run minus NP 50 times 20, say, for example, then you would have this guy over here put it out several times. Okay. Okay. Now I'm not looking at what happens next. Okay, but let's try to run this on several processes. Say, for example, I run this on 4 processors. So minus NP4 means run the following program on 4 processors using MPI, and I just call main. Right? So this is MPI run is installed together with MPI whenever you have compiled OpenMPI. And by the way, the code here is compiled using MPI-CC. So it's compiled using being aware of what is the communicator comparator which is in the background, what is the hardware that is running on your computer. And so this is exactly the way that we're going to run this. So if I run this now, what's going to happen here is I'm processor 3 or 4, and I'm running on Bulgari LAN 0 or 4, 1 or 4, 2 or 4. And then there's another thing that is written over here. Okay? So let's try to understand what has happened now. The thing is that has happened is that MPI run has actually created 4 instances of the same program, which is called main, and there are 4 independent instances, and they could be run on principle on different computers. This is taken care by the code, the MPI run utility. It's not taken care by you. So it's MPI run unless you specify at the command line some options that tell you explicitly only run those locally, allow this. There's several other ways you can explicitly tell MPI where to run these things, but this typically is taken care of by the system administrator. So if you have several processors in which you can run this code, MPI run minus NP total number of processors that's been allocated to you will run the code for you in this particular case. So let's not go into too many details there. What you need to know here is that this command over here has just executed 4 identical copies of main, and it has passed to each one of these identical copies of mains in some way, maybe, for example, using environment variables, for example, the rank and the size of the MPI communication world that is around. And you can query those guys from within the program. And as soon as you query these guys from within the program, you will know that there exist size processes which are identical to you that are running on the background. And then you can coordinate with these guys and do different works for different processes. And this is exactly what is happening here. So for example, here, if the rank is 0, so only if the rank is 0, what I'm doing is, so this is not a line, sorry, it was not very nice to look at. If rank is 0, I'm going from 1 to size, and I am waiting for something. Okay, so I receive value, and I want to receive one value of doubles from anybody that wants to send me one double, and I use tag 0 to basically identify what type of communication I want to do. And I'm using this MPI communication world and check the status over here. Okay, so what I'm asking here is that for every one of my partners, so from 1 to size, what I do is I initialize this MPI receive call. This is a blocking call in particular, and I wait for a value from any source, okay? And then I just return here. I write exactly what I have received from each one of the sources, okay? So what am I doing here? I'm doing something stupid and something trivial. I'm simply running this guy on each one of the other processors. So on each one of the other processors, I'm just sleeping for 3,000 milliseconds. I'm picking up a random number, which is initialized with the rank that I have, and I am returning this double number, which is just a random modulus 1,000 divided by 1,000, and I am sending this guy to destination, which is processor rank number 0. Okay, so this is the essential idea. The essential idea of message passing interface library is that it gives you functions that allow you to communicate with processors which live possibly on a different computer, possibly on a different data memory stage. Here, the essential part that you have to understand is that the memory that you access to is not shared with the memory that the other process is accessing to. So you cannot access to the same vector, and you cannot access to the same things. You have to do things separately at these parameters. Okay. At the end of the code, I just call MPI finalize, and this is what the main function that I have here does through this call to MPI and it finalize. Okay. Okay. So the MPI hello is something that you should understand, but it gives you hints on how these things work in the background. Now I would like to try to change this and to make sure that we do the same thing for our Poisson problem, and we use parallel computations on our Poisson problem. Okay, so there's going to be a few changes that we need to do. So I will do these changes together with you on Poisson.h, and I will follow in order for that, in order to understand exactly how this works. What I will do is I will copy the step example, the DL2 library examples step 40 file, and I will analyze step 40 with you and try to understand what are the differences with respect to Poisson.h and Poisson.tc. Okay, so I will copy this step 40 here, and I go to step 40. I run make this clean. briefly. Let me. I wanted to have a stripped version of step 40, and I will just ask build up using bundle D2. This should work. Okay. Sorry. I think I used the wrong. Okay. Okay. So this step 40.cc is the one that I want to open on the side, and I want to take a look at before we try to do things. Okay. So the first thing that I notice on this file that I have open is we have Poisson.cc on the left and Poisson.h I will also need. So we have Poisson.h with all the include files of our Poisson file, and on the right I have step 40. Okay. So the first thing that I notice is that there's an include part here which contains generic linear algebra, and which is the one that is dedicated to parallel linear algebra. And this is exactly what we want to use for our code. So I just copy paste this part here, and then I'll discuss on the left Poisson.h and try to explain to you what is happening over here. So what is happening over here is that this allows you to use different types of linear algebra backbones, either PETSC or Trilinus, according to a define that you specify at the compile time, or according to whatever you have available at your disposal as an installation. So if you have the installation and if you're running into Locker, you have both, so you can experiment with both. If you want to use PETSC or Trilinus, then you have to define, for example, force use of Trilinus, and this will use Trilinus instead of PETSC. Otherwise, this creates a namespace which is called LA, that is a alias namespace to DL2 linear algebra PETSC or to DL2 linear algebra Trilinos, what they have used for series of Trilinos. Okay, so with this, then we have to understand there's a long list of things that might be needed here. The first two that come to mind are the distributed triangulations and grid refinement. So if you write those here, you will see these two parts are distributed triangulation and grid refinement. And instead, all the various linear algebra classes that are written here are included with the distributed linear algebra class that was defined over here. Okay, generic linear algebra.h. So with the generic linear algebra.h, you include everything that is needed for this class for step 40. And for the parallel part, we need to use a distributed triangulation instead of a parallel distributed triangulation instead of a triangulation. So if you now look at step 40, the definition of step 40, it looks very similar to our Poisson problem. Okay, so there isn't much more except one, which is called MPI communicator, that is initialized before everybody. And this guy will do before the timer output, which is this MPI communicator that we have over here. And then instead of having a triangulation, we have a parallel distributed triangulation. So this object here will use, instead of a serial triangulation, a parallel triangulation. Okay, so this is the one biggest change that you have to have. And then, as you see, there's two objects which are called locally owned DoFs and locally relevant DoFs. And instead of having sparse matrix double and sparse and vector, we have LA MPI sparse matrix and LA MPI vector. And incidentally, there is no longer a sparsity pattern appearing here. So we have to change a few things, not at this stage, but we have to change a few things at the stage of the linear algebra classes. So if you go to the linear algebra classes, which we had defined here, after the constraints matrix, we have the sparsity pattern, sparse matrix, solutions, and system right-hand side. I will do the following things. I will simply call this and locally relevant solution and solution. I want to have both at my disposal. So I replaced system matrix, sparsity pattern, solution, and system right-hand side with the things that were present in step 40. And I need to have two index sets that actually identify what we need for local degrees of freedom. Okay, so this is only needed changes for MPI. Okay, so what I'm doing here, I am basically replacing everything that was in serial with something that now will work in parallel. So the first thing to notice is that triangulation now is a parallel distributed triangulation. So this will need to be constructed using a different argument with respect to what we had before. So previously, the triangulation didn't require any argument to be initialized. Now, this requires an MPI communicator to be initialized. So in particular, we use as MPI communicator, and you can see this in the constructor. We will do this in the constructor. So the first thing that we do here is MPI communicator is initialized with MPI convert. And this gives us the global communicator. And then I will copy the initialization that is created on step 40 to be consistent with what step 40 does. So I will initialize the triangulation and the MPI communicator the same way. And of course, this needs to be done with the same order in which things are defined in the include file. So I have that the timer is specified before the triangulation. And here One important part of things is that I don't want to output things for every processor. So I will be using something which is called conditional output streams, which is here indicated with PC out. Okay. So this is created before the computing timer and right after the MPI communicator. And I will initialize the PC out with the same way that it's initialized here, and I'll tell you exactly what this does. So what this does is the following thing. So it initializes a output stream that is only active when the MPI communicator tells you that this MPI process is process number 0. So I take process number 0 and I give process number 0 the honor of telling me things about the program. And I will just ignore the output of everybody else. So this output is going to be initialized, and it's going to be, it's called conditional stream. If you look at the way this is initialized, conditional off stream, the documentation tells you that this conditional off stream is only active when the second argument is set to true. If it's not set to true, then this is basically a black hole in which nothing gets written out if you write out this. So this is used to replace stdc out in C++. Okay, and instead of using stdc out on the timer, I will use the conditional out stream. And every time I have an stdc out, I will make sure that I use the conditional out stream. Okay. Now with this, I should be ready to build, and I will have some problems with the initialization of the vectors because those vectors need a different type of constructor in order to be built. Okay, so sparsity pattern is not defined, so because I have removed it. So sparsity pattern DSP, I should have here a dynamic sparsity pattern that is created. And as you see, as soon as I've created a sparsity pattern on step 40, so this part over here makes sparsity pattern, uses an argument which is called locally owned DoFs in the DoF handler. Okay, so before we do that, we need to understand how to store the locally relevant DoFs and the locally owned DoFs locally. And we actually have these two variables that we created here, locally owned DoFs and locally relevant DoFs. And before we do anything, right after I have distributed the degrees of freedom, I want to output some information about those guys. So let me replace every stdc out with PC out in the poisson.tc. And when I'm here, I will create the locally relevant DoFs by extracting those two guys here. So locally owned DoFs, after I've distributed, I extract the locally owned and the locally relevant DoFs from this guy. Okay. One of the exercises will ask you to actually inspect those with locally relevant and the locally owned DoFs, which are those guys over here. And I urge you to do so as quickly as you can, because this allows you to understand exactly what is happening. So in particular, the number of degrees of freedom that are associated with this object is going to be distributed unevenly, and you should be able to see this even with simple triangulation. Okay, so if you look at the way those functions are constructed, the only thing that is different at the moment between step 40 and our poisson.cc file is the construction of the sparsity pattern. So the sparsity pattern needs to have access to the locally owned DoFs. So instead of having using the DoF and the locally owned DoFs, I'll just use the variable that we just filled up. And it needs to have access, sorry, not after I've created it. So you create the local sparsity pattern, and then you distribute the global sparsity pattern using, we already extracted that, so we don't need to call that. And it needs to know about who are the locally owned DoFs and who are the locally relevant DoFs. Okay. And now we don't have anymore the sparsity pattern, but the matrix needs to know not just the sparsity, which is the sparsity that is used over there, but also what are the locally owned DoFs. Notice the matrix doesn't know anything about locally relevant DoFs, just the sparsity and the DSP. So DSP, which is the dynamic sparsity pattern, needs to know about the sparsity, needs to communicate what are the constraints, and that's why we need to distribute these guys using that code. And now I have solution and system right-hand side. And let me show you how these are initialized here. So this we have locally relevant solution and system right-hand side. So let me copy these initializations here. We have locally relevant solution, which is initialized with locally relevant DoFs and locally relevant DoFs and MPI communicator. While here, the other two guys should be initialized with the MPI communicator and the locally relevant DoFs alone, while we keep the error per cell exactly as it was before. Okay, so let me spend some time in understanding what this code is doing and what this code is doing differently with respect to that. So these two guys, locally relevant solution and solution, which is this and that, those two objects are thought to be writable objects. And in particular, what I'm telling to these objects, so locally relevant DoFs is an index set. If you look at the definition of an index set in the O2, it is a data structure, which is an efficient data structure that is very efficient to communicate around, that contains several information. So first information it contains is what is the global size of the vectors or the global size of the set that you're looking at. And it contains all the subranges of elements, not necessarily contiguous, that are owned by the current process. So it represents what the name says, a set of indices within a larger number of indices. So usually you use this to identify what are the locally owned degrees of freedom on the current element. So here, this is exactly what is needed to initialize vectors and matrices. Those vectors and those matrices do not contain the global number of degrees of freedom, not 1 billion degrees of freedom, but 1 billion divided by the number of processors, roughly. And of those 1 billion divided by number of processors, you need to identify which ones are the ones that you actually have locally residing on your local memory. And all the others will reside locally on some other memory. So the union of all those index sets will contain all the indices between 0 and the number of degrees of freedom. And this is what happens on solution, right-hand side, and matrix. They own, if you look at the union of all of those guys on all the processors, this will be identical to the matrix that you had before in serial. But if you look at this from the local perspective, you only see a fraction of the global degrees of freedom. You only see a fraction of the indices. And those fraction is specified by locally owned DoFs, which is an index set. On the other hand here, I need to have access not just to the locally owned DoFs, but also to the locally relevant DoFs. So in this particular case, I have to be careful because this locally relevant solution here only owns these guys, but in order to have access to the guys that are over here, you need to actually communicate with other processes. So once you initialize these locally relevant solutions, this can no longer be written into. So the idea here is that solution and right-hand side are write vector, and this is a read vector in the sense that you can only read from these guys, but you cannot change the entries of this guy, because in order to read these guys, you need to communicate with other processes. And on the other hand, you can write in this also in places where you don't actually have access to, provided that you communicate with other processes that you have finished writing into those places. So there's two different approaches in which you access those guys. Okay, so let's try to build. This should actually compile. And if you run this, you're going to have a lot of errors and a lot of problems, and we will see exactly what those type of errors and problems are. Okay, so the first problem is in the solver that we have. And in the solver that we have in line 315, I have a sparse static solvers, and this is no longer possible because we are not in serial anymore. So we will just have this object over here. And now, instead of having a solver CG with vector double, we have a solver CG with LMPI vector, which is what we're going to be using. And this is going to be, let me show the AMG preconditioner, the way this is used in the step 40. So in step 40, we have a solver control, and we have a LA MPI precondition AMG, which is this guy over here. Let me remove that. And I'm assuming that this is going to be defined for everyone. Okay. And we assume, I don't want to use any additional data with respect to what we had before. So let me just eliminate that and use LA MPI precondition AMG instead of the other ones. Okay. Okay. Now, the constraints distributed solution here will have distributed the solution. And as soon as I've finished with this, I can communicate to all the processes what is the locally relevant portion of the solution. Okay? And I will do this here. And this is done by doing locally relevant solution equal solution. Okay. If I try to run this right now, what's going to happen is that some of the classes that I have constructed will throw an error. And the reason why they will throw an error is because in some cases, for example, in the error estimator, I am trying to compute errors, and I am trying to evaluate the solutions, or in the output, I'm trying to evaluate the solutions in portions of the domain which I do not own, or portion of the degrees of freedom which I do not own. So if you look at the ways, the things that I have changed so far, so let's try to take a look at the changes in the Poisson class so far. I have added stuff for outputs, like in the Poisson communicator. And so far, the other changes that I did is the initialization of MPI vectors separately. Okay? In principle, if I go to the build directory and run this in serial, this should still run. So this should still give me something. Okay? Of course, if I try now, in principle, it should run, but it doesn't, because there are some issues here which are not working. Okay, so let's try to understand what the errors are that we are seeing, and in particular here we have some PC setup hyper, PC setup preconditioner AMG. Object is in wrong state. Okay, so the object is in wrong state. It means that I have not compressed, or I have not communicated all the various things at the end of the assembly processes. So far, I just assumed that everything was done in the correct manner, in the similar way that we did in the serial case. But of course, this is not the case, because I still need to communicate to the various processors once I have finished assembly. For example, in the assembly routine, I have a call which is in the assemble routine, assemble system. What I do here is I call workstream run between begin active and end active. I assemble on one cell and then copy the one cell. At the end of this, what I know is that the system matrix and the system right-hand side have been assembled also for some parts which I do not own in principle. In particular, if I look at the assembled system one cell in the class assembled system one cell, what happens here is that I loop over all local degrees of freedom. And these local degrees of freedom include, for each cell, as I showed you in the previous in the presentation, for each cell, they also include parts which are not locally owned by me. For example, if I include, if I loop over this cell and assemble things, I will have as a global index also the blue guy over here, which I do not own. So the local object will store, when I do that, and I sum into the vector of system right-hand side objects which pertain to this index over here, I will not get an error, but this object will not be communicated to the blue guy until I explicitly say so to the vector. So once I finished assembling things, I need to communicate to all the other processors that I have assembled something on this blue guy or on that blue guy. Okay, and this is done through the two calls to system matrix compress and system right-hand side compress. Okay, so right after I have assembled the systems, I have to call this two guy, and if I want to be sure that everything is working correctly, I cannot assemble on old cells. I have to make sure that I only assemble if the cell is locally owned. If I do this at this level here, this is an issue. This is an error, and it's a problem because it means that I'm going to looping over all cells even when it's not needed. And I'm going to be doing this copy on all cells even when this is not needed. So the essential part here is that the assembled system needs to run on, let me call this assembled system serially in this case. So we don't do it the way that we did before. So we are going to do this assembled system not using workstream run, but using explicitly the same thing that we were doing before, which is this. Let me call this const auto and cell in DoF handler active cell iterators. This loop here is equivalent to the serial version of the assemble system that we had before with assemble system one cell. And what I'm doing now, let me eliminate the mutex, which is not necessary for the moment. What I'm doing now is before I enter in the loop, I have to check that this cell is actually locally owned. And this is the only difference with respect to the serial code that we would have to do in this particular case. So I'm looping over all cells, and if the cell is locally owned, then I assemble it. Otherwise, I don't. Now, of course, this is going to assemble just one portion of the matrix, but I'm sure that processor number 2 is going to assemble the other portion of the matrix if I run on two processors. And the idea is you split the work at the level of the cells. You don't split the work at the level of the degrees of freedom. So you may have locally that the copy one cell tries to write into a portion of the code that you don't have access to. And these two calls over here, 346 and 347, make sure that you actually generate the correct result. And now, if you look at this, Poisson seems to have run correctly. So let's do Poisson with the test.prm as an input file, and then a code test.prm. Open that. Actually, CP used last use parameters to test PRM, so we only have the short version. If I run a couple of refinement cycles, say 3 here, instead of 1, I should be able to run test PRM for 3 cycles. And this seems to have run correctly. I mean, of course, I'm not computing the correct error, but I'm not checking the correct estimates, but it seems not to have had problems in running. And so far, I'm running on 1 single process with number of threads equal to 1. Okay, so let's try to understand how to make this work differently. So if I call now MPI run minus MP2 and try to run this code, this should not be run correctly. I should get some errors somewhere. Yeah? And the errors that I get are related to the fact that in some of the functions, I will try to access objects which are not available for me. Okay. An example here, let's struct subvector 2 constant forward iterators, so on and so forth. This exception usually indicates that some condition with the authors of the cause. Okay, this doesn't say much. However, we know, I think, well, we know where the problems might happen. And the problems might happen in 2 parts. In the estimate part, which is this guy, because we call integrate difference with a solution vector. And this solution vector, for sure, does not contain all information that we need, because this solution vector only has locally owned indices, not the locally relevant indices. So here we should use locally relevant solution instead of locally solution. And the estimator also should have locally relevant solution here. And the Kelly error estimator that I have here also needs to make sure, if you look at the way step 40 is run, so we have Kelly error estimator, yeah, needs to run on the locally relevant solution, on the locally relevant solutions. And now, one has to be careful here, because as soon as I have done this, what I will have at my disposal is an object which is error per cell, and this object will contain error per cells on the active cells of the current triangulation, including all the cells which are artificial. So I have to be using a different type of grid refinement strategy, and it's not the grid refinement in the serial version, but it's the parallel distributed grid refinement strategy. So the only thing that needs to be changed is that instead of using the grid refinement, which is written there, I have to use parallel distributed grid refinement, parallel distributed grid refinement. With this change, we should be almost up and running, almost finished. There's still one important issue, which is the output issue. Okay? So the output of our triangulation is still not there. So we still need to have the output written in the correct manner. Okay? But as you see, the number of changes that I had to do are not so many. Okay? So the number of changes that I had to do is very limited. The only thing that needs to be done is exactly to use a locally relevant solution. Then in the outputs parts, I want to have here locally relevant solution. And also interpolated exact has to be equal to the locally relevant solution. So it's the same object of type locally relevant solution, otherwise things will not work. And so we have to do the same thing for the locally relevant exact solution, which is now set equal to the interpolated exact. After we created it. So I want this to be done only on the locally. I want to be able to do to plot this as well. And then we have the error per cell, and this should all be correct. The only thing here is that now if I output on the VTU, this is not going to work because the VTU file that I have here is going to be written by multiple processors at the same time. So they are going to overwrite each other all the time. So there's an object which is called write VTU in parallel, which is this guy here. And this writes the solution from all participating nodes to a single compressed VTU file on the shared file system. So this will take care of writing everything in parallel, and it needs an MPI communicator to do things for you. Those are the three changes, the few changes that needs to be done in order for this to work. Oh, sorry, this needs the file name, not the actual file store, because it needs to initialize internally parallel IO writing using MPI. Okay. So this isn't much, and of course, if you want to understand exactly what is happening in the background, I urge you to actually read very carefully about step 40 and to read exactly how step 40 works. But at this, so at this stage, we have this with test PRM that seems to work. And then let's see whether MPI round minus LP2 plus some with test PRM works. This doesn't seem to work. So let's see. Okay. I'm looking whether I forgot to do something. Okay. Let me use, for this particular code, let me use Trilinos, because I think it has better output. It has better outputs. So let me see whether I forgot to use, yes, I did forget to use this. Locally relevant solution, that's the guy. This is locally relevant solution. Error table, locally relevant solution. Okay. So basically, every time you need to read from the vector to compute something, like errors, like error estimators, like to output data, you have to use the version of the vector that contains locally relevant objects. And otherwise, you have issues with non-locally owned objects. So now I'm just trying to check whether we did this correctly everywhere. So this is going to write in the solution, so everything is fine. And then after I distribute the constraints, this is going to write the solution there. I think the constraints may also be something that need locally relevant DoFs. This I forgot, so I need to initialize the constraints for locally relevant DoFs. And so that it knows that it has to communicate about the locally relevant degrees of freedom. That's it. Okay. So this is an error that I'm looking at. So if you look at this, it tells you exactly what is happening. So PETSC was not so clear in the error that it was shown. So here it says there's an error occurred on line blah, blah, blah of Trilinos vector.cc. And this tells you that I tried to access using operator parentheses the vector, an entry of the vector, and the condition was false. You try to access element 58 of a distributed vector, but this element is not stored on the current processor. Note, there are 136 elements stored on the current processor from within the range 153 through 288, but Trilinos vectors needs not store contiguous ranges on each processor. Not every element in this range may in fact be stored locally. So here, most likely, I forgot to use a locally distributed solution vector to access the, when I try to access an object. And I would like to understand where this has happened. So here, this is shown somewhere in the build patches, parallel data out, implementation. So workstream run, parallel data out. So it looks like where this is happening is in the build patches of the data out class. So probably when I output results, I forgot about something that I should not have forgotten. So let's remove for a moment the exact solution. And let's see whether that was the problem. Because I have the locally relevant solution here. So this should actually have worked. Okay. Yes, that seemed to have been the problem. Okay. So just to make sure that everything works correctly, let's try to open this with ParaView. And we have the files Poisson BTU, and let's see what the output looks like. It should be identical to the other. Let me see in test PRM output file name use Poisson. Yep. So we should have nonlinear subdivision levels equal to 4. And let me see in the test PRM. This has been written a few seconds ago, so I'm assuming this is correct. Reload existing files. It seems to have generated something reasonable. So let's see here. I'm not sure it's correct. So let me eliminate this. Let me eliminate everything that has been created. Let me do MPI run minus MP2 plus 1. Okay, so somewhere I forgot to say that I want to output the table on PC out. So this should actually be filtered, so it should not be on just on the output. Conditional string should tell me if it's active. So if it's active, it means that we are on processor 0. So we only output the table, the error table on processor 0, otherwise things become complicated. And I'm using test PRM with final element d equal to 1, hypercube, and regenerate the function. Oh, it hasn't finished yet. Okay. So now I have Poisson 0 VTU, Poisson 1 VTU, and Poisson 2 VTU. I'm not sure why it's still trying to run using hyperbole. So I'm not understanding why I keep seeing a hyperbole with degree 2. Does any one of you understand why this has happened? I am confused. Ah, I know. I'm in the wrong directory. This is not lab 7, this is lab 8. Ah, okay, guys, sorry. I was really, for a second, I thought that I was getting mental. Okay, it's probably true, but at least I know what's happening. Okay, so this seems to be the correct solution when you have a unit right inside. I think I have force an expression equal to 1, and estimator type is equal to 0. And there's nothing more than I want to write here. Let's say now I want to write BTK, and I want to obtain a description of the triangulation. Write mesh per processor as VTU. So this is the file that I would like to generate. The same type of things that you saw in the triangulations. And I want to show this to you in order for you to understand exactly how this is created at every, what's the level, how this is generated at each. So let me go to the refined grid. After the refined grid, I want to grid out write mesh per processor as VTU. So we want to have triangulation. I want to write this on a string which is called tria. And I want to include artificial levels. And I want to view levels false. We don't need levels. Okay. So I'm going to write false here and true. Okay. I would like to show you what this triangulation looks like when you run in parallel with 2 degrees of freedom, and when you run this with several refinements. And actually, let me do this externally, and let me also use one per cycle, because otherwise it doesn't look like on the output. The output results, I will do this at the end. All right, mesh per processor, and this instead of being tria, it will be tria plus std to string cycle. Okay, so this is going to be 3-0, 3-1, 3-2, 3-3 for each one of the cycles, and I want to actually see how this works. And let's make this more interesting. So we make this with number of refinement cycles equal to 5. And instead of marking strategy, we do Kelly. We do fixed fraction. And instead of estimator type exact, we do Kelly. Okay? So we do Kelly our estimator on that. And instead of doing hypercube, we do hyper-L, which is a little bit more interesting. And if you look at the hyper-L documentation of the grid generator space, we need left, right, and then colorize. That's perfectly fine, should work as it is. And with this, I should be able to see something interesting, let's say with 3 processors. And let's see whether this is actually interesting or not. It's not. For some reason, it has not written this. So I have to check.
Before you used it. Can we edit again because there was an error?
Oh, in the build?
Yes.
Oh, okay, thank you. That's why I was not seeing it. Oh, grid out is not defined, of course. And the computer is always right, so you need to know what to include when things happen. Thanks, Ivan. And I'll just take a quick look at this, and you are absolutely right. So this should be grid out, GO, and then GO dot right mesh. Yep. Okay, now I should have a different grid. So this is a hyperhel triangulation now, on which I forced a one constant forcing term, and it's locally refining across the singular parts. And now I would like to open the triangulation part, which is written here. And as you see, this is written in several processors. Yeah? So there's Tria, Proc0, Proc1, Proc2, and Tria, Proc2, and the various processors. So if I open this triangulation and look at it globally, it looks like a classical triangulation with several differences. If you look at the level subdomains, this triangulation is split into three parts, and you will see the triangulation on processor 0 for all refinement levels. And now I want to see triangulation on processor 1. So that's Proc0 and that's Proc1, for example. And I see surface with edges. And now this is a triangulation on processor 1. Okay. And as you see here, the proc writing, so subdomain, yeah. Now you should see the same type of triangulation output that I was showing in the slides. And those is exactly generated with the slides. So this is telling you that this is the subdomain for that. And then this is the neighboring cells that is actually being used by this subdomain procedure. Of course, the splitting here is not very efficient in the sense that it's generating two disconnected subdomains. But this is going to be, it's true because the number of the processors that I've used is a very awkward number. So it's number 3 in this guy over here, even though that would have been perfect by splitting this guy as 1 processor, 2 processor, 3 processor here. This would have been the correct choice. But of course, this is due to the fact that I'm using a space filling curve, and that depends on how the space filling curve is defined. It doesn't depend on other processors. Okay. And of course, I can also open the last one. Surface with edges. Processor rising is not processor rising, but subdomain. Yeah, there we go. And now if you look at this as a subdomain ID, the subdomain ID identifies the processor. In this particular case, this is number 2. So this is the first processor that I have there. And of course, if you overlap them, you will see the full triangulation with the various subdomains written on top of them. And of course, you can do that by actually opening the Tria PVTU. And if I now look at this with edges, these are all overlapped. So you should be able to do opacity here and put the opacity, which is slightly smaller, and use as level subdomain the color. And then go to that. This should show the full triangulations in the background. I think. Yeah, level. Sorry. So there's a lot of mess going on here. So you have to play around with this guy over here. You have all the information in all the triangulations that is written there. So this doesn't do exactly what I was expecting to, but it's roughly correct. Okay, so let me stop here. Do you have any questions? So let me just finish by quickly showing you the changes that I had to do in order to make this parallel. So I had to include in the header file 3 more header and define this part. I had to change the definition of the triangulation and the definition of the vectors, and include index sets to be locally owned vectors, and that was it. And then if you go to instead to the Poisson.cc file, you have, well, from the grid out, initialization using MPI communicator for the triangulation, for the timer, and for everything that actually outputs some things. And then initialization in the setup system, I need to extract the locally owned DoFs and the locally relevant DoFs, initialize the constraints with the locally relevant DoFs, construct the sparsity pattern passing locally owned and locally relevant DoFs, initialize the matrix solution system right-hand side with the owned DoFs and a locally relevant solution with owned and relevant, and eliminate every time that I need to read from the triangulation, I need to read using locally relevant. And this I did using not work stream, but using a full loop of the iterators. We could do that also to have a hybrid parallelization strategy. And I didn't actually show you how faster this is, but if you test this with MPI minus NP run equal 1, and wall time is now 3.86, and if I do MPI run minus MP4 is 1.44. So it's roughly a fourth of what I started with. Okay. Of course, there's a lot of things that are going on here, but if you look at the total times, this is 0.14, and then if you look at the CPU times before, that was 0.484. So this is the same thing as before. Okay. So it's 1/4 of the other one. So the assemble system has become 1/4 faster, and all the rest is a little bit faster as well. Okay, let me stop here.